For the exercises, there's one thing I've asked you to do that really is extremely important. So I wanted to discuss it a bit. So I've started off here. I've written down the mode expansion for phi of x. And I've been very careful to write out all of the t and spatial x dependence. So remember, when we write down phi of x, x is some event, and it depends on t and x. This is then equal to an integral of the Lorentz invariant measure. We've got alpha k, e to the minus I omega kt plus I k dot x. We've got a second term, which is alpha k dagger, e to the plus I omega kt. Oh, there's a typo. This should have been minus I k dot x. Good. Okay. So that's the form of phi. Now, let me... The other thing I will want is an expression for phi dot. So phi dot of t of x. So what does phi dot mean? Well, I've taken a derivative with respect to t. So look at that mode expansion. Where's the t dependence? It only sits up in the exponent. So when I'm taking the t derivative, well, doesn't do anything to the measure. So let me put the measure in. Integral d3k over 2 pi cubed to omega k. That's left invariant. It doesn't hit alpha k. There's no t dependence there. Now, it will hit the exponential. And what does it do? It brings down minus I omega k. And then we've got e to the minus I omega kt plus I k dot x. Now, let's look at the second term. We're not going to hit alpha k dagger. We will hit the exponential, and we'll bring down e to the I omega k. And then we'll have the exponential sitting here. I omega kt minus I k dot x. So that's the answer for phi dot. Make sure that you're happy with that. The task that I want to consider now, and this is the thing that is so important, is we now want to solve for alpha k and alpha k dagger in terms of phi and phi dot. So I want a formula for alpha k and alpha k dagger as functions of phi and phi dot. Now, if you look at the formulas above for phi and phi dot, the formulas for phi and phi dot look like we're taking a Fourier transform. Okay, so why do I say that? Well, you've got an integral over momentum. That looks like a Fourier transform. And you've got things like e to the I k dot x or e to the minus I k dot x. That looks a lot like you're doing a Fourier transform. So a natural thing to try do to solve our problem, to figure out what is alpha k and alpha k dagger in terms of phi and phi dot, a good thing to try is try to take the inverse Fourier transform. Okay. Now, I don't know if this is going to work, but the good news is if it doesn't work, we can just erase the equations that we've written and start again. So let's just try it. So what should the inverse Fourier transform look like? Well, it'll be an integral over x, and I'll put here e to the I p dot x and phi of x. Okay. So now let's plug in this mode expansion. So we'll have an integral d3x, an integral d3k over 2 pi cubed 2 omega k. Then we'll have the alpha k. We'll have e to the minus I omega kt plus I k dot x. And then we will have from this e to the I p dot x, we will have plus I p dot x. Good. And then for the creation operator term, we'll have alpha k dagger, e to the I omega k t minus I k dot x. And then again, from the e to the I p dot x multiplying phi of x, we'll have plus I p dot x. So I've only done a very trivial manipulation. Now, I have two integrals to do, an integral over x and an integral over p. In fact, the integral over x is easy to do. Why? Well, take a look at where the x dependence is. So we're going to try to do the integral over x. Where is the x dependence? There's x dependence sitting here and here in the first term, and there in the second term. So the x dependence sits only up in the exponent. We have a very nice integration formula. So this is a formula that you really should know off by heart because it's so useful. And it tells you that an integral d3x of I q dot x is equal to 2 pi cubed times by delta of q. A few things to notice. If you were to complex conjugate this equation, you would learn that the integral d3x of e to the minus I q dot x. So complex conjugating, the 3x stays the same, but the exponential changes sign. 2 pi cubed stays the same because it's real, and delta of q stays the same because it's real. And the reason why the right-hand side of these two identities is exactly the same is because the delta function is an even function, okay? So that's another thing to bear in mind. So you don't have to bother too much about what is the sign in the exponent. You're always going to get a delta function, and don't forget about the 2 pi cubed coefficient. By now, these 2 pi cubes should be looking pretty familiar to you. They've appeared a few times, and we've even put them into our measure because of the way the 2 pi cubes appeared. Okay, good. So now let's keep going with our integral. So this is sort of an aside. Okay, so that's just formula that we're going to use. So what is our integral equal to? Well, we're not going to have integral d3x. We're not going to have that integral d3x anymore because we've done the integral over x. We'll still have an integral d3k over 2 pi cubed to omega k. And then we will have alpha k e to the minus I omega kt. And then now comes the bit from the x integral. So let me put it in red so that you know where this came from. So just looking at this, when I do the x integral, I'll get a 2 pi cubed. And then I'll get a delta function of whatever's multiplying x. And what multiplies x? Well, it is k plus p. Good. And then plus the creation operator term. This is alpha k dagger. We've got e to the I omega kt. And then again, the x integral. So let's again put this in red. We will have a 2 pi cubed, and we will have a delta of k minus p. Now, this is great that we've got these delta functions because they make the integration over k very easy to do. So the first thing that will happen is this 2 pi cubed will cancel against that one, and likewise for that 2 pi cubed. So all of the 2 pi cubes cancel. Then the delta function sitting in the first term is going to set, so everywhere you see a k, you should set that equal to minus p. And the delta function from the second term, whenever you see a k, you should set that equal to p. And then the last thing that I want to remind you of is that omega of minus k is equal to the square root of minus k dotted into minus k, that's the dot product, plus m squared, but minus k dotted into minus k is the same as k dot k plus m squared, and that's just omega k. Okay, So omega of minus k is equal to omega of k. I'm going to freely use that. Okay. So now what do we get? Well, I'm actually going to do the integral over d3k. So I will have, from the first term, I will have 1 over 2 omega p, would it be minus p, but omega minus p is equal to omega p. Then we'll get alpha p e to the minus I omega p t. And from the second term, we've got 1 over 2 omega p alpha p dagger e to the I omega p t. And let me just make one more comment. The oscillator had, well, so alpha k was indexed by a full momentum k mu. And this is equal to omega k and spatial k. But if you set k equal to p, well, what does this become? This becomes omega p, comma, spatial p. Okay. I should be a little bit careful. In the first term, I set k equal to p. So let me put a tilde on this alpha. I'll leave that one normal. So p mu is omega p comma p. P tilde mu is equal to omega p comma minus p. And I need that because in the first term, the term with the annihilation operator, I actually set spatial k equal to minus p. Good. So this is the answer that I've obtained for doing this integral. Good. We'll continue in a moment.